calculating the energy change in a nuclear reaction from the mass change. Okay, so what we need to do is add up the mass in AMU of the reactants and the mass in AMU of the products and work out the difference. If mass is gained, that means we're gaining mass, we're absorbing energy. If mass is lost between the reactants and the products, that means we're ejecting mass, which means we're losing energy, we're emitting energy. So the mass of the reactants then, our reactants are plutonium-239 and helium-4. So if we look in uh, atomic mass units, that's 239 plus 0.522 AMU plus the helium is 4.00260 AMU. And you may have more information than you actually need, just as an FYI. So that comes out for our mass of our reactants to be 243.0548 AMU. All right, so the mass of our products then is going to be our products is californium 242, so that's 242.0588, and a neutron, one neutron, so 1.00866649 AMU, AMU, giving me a total of 243.067. 4649 AMU. We're just going to leave all those ugly decimal places for a moment. We'll tidy up later. All right, so then let's see. The delta M, the mass difference, is going to be. I'm just going to draw a little delta for the difference in mass. If I do products minus reactants, final state minus initial state. So that's going to be 243.06744649 AMUs minus 243.0548 AMU. If we give a mass difference, if it's positive, that's going to be energy being absorbed, and we do get positive 0.01266649 AMU, and that is going to be absorbed because the products weigh more than the reactants. All right, so I guess that answers the first part of that question. Absorbed. So how much energy is absorbed or released? So we need to convert mass to energy. So that is that infamous Einstein mass energy relationship. Technically, it's the change in energy equals the change in mass, which we just worked out, times the speed of light in a vacuum squared. So that is delta M and then C squared. So we know that one, right? So caveat then, if we want energy in energy units, that's joules, we're going to want mass not in AMUs, right? We're going to want to have mass in kilograms, okay? Because what are the SI units of joules? Kilograms, meters squared per second squared, right? So we need to get that mass into kilograms. So there are some unit conversions that are going to help us with this. So first of all, if I can remember, 1 AMU equals 1.66054 times 10 to the power of minus 27 kilograms. That's going to be helpful. And then, of course, we want per mole, we need the Avogadro constant. The Avogadro constant is, again, off the top of my head, 6.022 times 10 to the power of 23 per mole. Of course, if you get more sig figs in your ALEKS data book thing, you should totally use them. And then I also noticed, and this is going to come in later, we're going to need to convert into mega electron volts. That's the physicist's favorite unit. So we do need a conversion factor between joules and mega electron volts. So I'm just going to put this one here for later. 1 mega electron volt is 1.60 218 times 10 to the power of minus 13 joules. Okay, so now we've got those squirreled away. We can go ahead and do some calculations. All right, so the first thing we're going to need to do is convert that mass in AMUs into kilograms. So I'm going to take that 0.0126649 AMU. And to get that into kilograms, then I'm just going to use this as a unit conversion factor. So that's 1.66054 times 10 to the power of minus 27 kilograms. That's going to give me my answer in kilograms. That comes out to be 2.103. I'm just going to keep all these decimal places for a mark. Well, I know it's just ugly, but 10 to the power of minus 29 kilograms. So then that is what's going to stick into my Einstein mass energy relationship. So my change in energy is going to be my change in mass. So it's the 2.10 blah 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 times 10. 3055 times 10 to the power of minus 29 kgs times speed line of vacuum 2.9979 times 10 to the power of 8 meters per second. So that's going to give us our meters square per second square because we are going to square all of this. And that will give us energy in joules, which comes out to be 1.8901 times 10 to the power of minus 12 joules. Now, that does not sound very impressive, and that is because we are not there yet, okay? We're asked for the energy in kilojoules per mole. That is the energy of one nucleus of polonium-239 reacting with one helium-4 to form one curium-244 and one neutron. We are talking on like the one atom to one atom like ratio here, okay? So first things first, let's get joules into kilojoules because we know we're going to need to do that. So we're just going to 10 to the power of 3 joules. That is going to be, oh, I can't type. Oops, my bad. Very conscious we might run out of space here. So in terms of kilojoules then, that is going to be 10 to the minus 15 kilojoules, cheating a bit there. Okay, so now we got our mass in kilojoules and we want kilojoules per mole. So what do, dear reader? We're going to multiply by the Avogadro constant, right? So times 6.022 times 10 to the power of 23 per mole. See what we do there? That is going to give us kilojoules per mole. So that is going to be 1.138 times 10 to the power of 9 kilojoules per mole. Okay, so suddenly we're dealing in very big numbers, right? Like a billion kilojoules per mole, and that is why there is so much energy that can be released from the nucleus, right? Either, in terms of nuclear energy or, big bombs or whatever. So then we're asked to convert to mega electron volts. So we have a conversion factor between joules and mega electron volts, which means we need to go back to that 1.809. Sorry, 1.8901 times 10 to the power of minus 12 joules that we already worked out. And then we're going to convert to mega electron volts. So I always think they sound cool. Mega electron volts, like it's trying to impress someone here. So 1 mega electron volt is 1.60218 times 10 to the power of minus 13 joules. So my joules is going to cancel out. I'm totally going to run out of space in my text box. So stick that in your calculator and you should end up with about 11.79 mega electron volts. I don't know how many sig figs we need. I guess I could probably scroll down, find out. Let's see. Probably 3 sig figs. So yeah, about 11.8 mega electron volts, and that is all you need to do for that. So just be really careful of your units, okay? Remember, a loss of mass is going to be an emission of energy, and a gain of mass is going to be an absorption of energy. All right, take care, good luck.